Close your eyes, let your breath slow down. Tonight we're going to take the longest journey imaginable, not across an ocean or even across a galaxy, but all the way back to the very beginning of everything. Back before the stars existed, before the planets, before time itself had a shape. We are going to begin at a moment so extraordinary, so almost impossible to imagine, that scientists have spent over a century piecing together what happened. And yet, piece by piece, they have, and what they've found is one of the most beautiful stories ever told. This is the story of the Big Bang. Our story begins approximately 13.8 billion years ago. That number is so vast it's almost meaningless to the human mind, so let's try to feel it differently. If you compressed all of time from the Big Bang until today into a single calendar year, all of recorded human history, every empire, every invention, every war and discovery would fit inside the final 11 seconds of December 31st. That is how long ago our universe was born. And what existed before those 13.8 billion years? This is perhaps the most humbling truth of all. Before the Big Bang, there was no before. Time itself did not exist yet. Space did not exist. There was no darkness, because darkness is still something. There was simply nothing, no stage, no canvas, no waiting emptiness. And then, from that absolute nothing, everything came. In the very first instant of the universe's life, within a fraction of a second so small it has no name we use in everyday life, all of the matter and energy that would eventually become every star, every planet, every living thing, every thought ever thought was compressed into a single point. Scientists call this a singularity. It had no size, it had infinite density, and in that very first moment it began to expand. And here is something that surprises almost everyone who hears it for the first time. The Big Bang was not an explosion in space, it was an explosion of space. There was no outer void for things to explode into. Space itself stretched, and it has been stretching ever since in every direction, carrying everything inside it along for the ride. In those first billionths of a second, the universe was almost unimaginably hot, temperatures we have no everyday reference for. And yet, even in that chaos, nature was already beginning to organize itself. The four fundamental forces that govern everything in our universe today, gravity, electromagnetism, and the two nuclear forces, had not yet separated from one another. They existed as a single unified force. The universe was so hot, so dense, that matter and energy were indistinguishable, merging in and out of each other in a constant, boiling frenzy. Then, in a moment called cosmic inflation, something remarkable happened. Within the first tiny fraction of a second, the universe didn't just expand, it expanded with extraordinary violence, doubling in size again and again in an almost incomprehensibly short period of time. In less time than a single heartbeat, the universe grew from something smaller than an atom to something the size of a grapefruit. The forces began to separate. The universe was cooling, and as it cooled, it began to take on structure. By around 1 second after the Big Bang, the universe had cooled enough for something wonderful to happen. The first particles began to form. Protons and neutrons, the building blocks of every atom, blinked into existence. But the universe was still so dense and hot that light could not travel freely. Photons, the particles of light, were constantly colliding with other particles, scattering in every direction. The universe was opaque, like a thick, glowing fog, and it would remain that way for a long time yet. For the next few minutes, just minutes, in a universe that would go on for billions of years, protons and neutrons fused together in a process called Big Bang nucleosynthesis. This brief window of time produced almost all of the hydrogen and helium that exists in the universe today. Roughly 75% hydrogen, 25% helium, those proportions forged in the first 3 minutes are still visible in the universe around us, in every star, in every gas cloud drifting between galaxies. In a very real sense, the recipe for the cosmos was written in those opening minutes. Then came a long, quiet waiting. For roughly 380,000 years, the universe continued to expand and cool, but little else changed in the broad sense. The fog endured. Protons and electrons roamed freely, never able to bind together because the universe was still too energetic. And then, 380,000 years in, the temperature dropped to around 3,000 degrees. Electrons and protons finally slowed down enough to find each other. They joined, forming the first neutral atoms, mostly hydrogen with some helium scattered throughout. And in that moment the fog cleared, light was free. For the first time in the history of everything, the universe became transparent, and photons streamed out in all directions, traveling freely for the very first time. Those very photons, those particles of ancient light released 380,000 years after the Big Bang, still exist today. They've been traveling for nearly 13.8 billion years, and we can detect them right now all around us as a faint glow that comes from every direction in the sky. Scientists call this the cosmic microwave background, a kind of afterglow of the Big Bang itself, imprinted on the universe like a fossil of light. When astronomers first accidentally discovered it in 1964, they thought their radio antenna was picking up interference from pigeon droppings. It was, in fact, the oldest light in the universe. So here we are, barely 10 minutes into our journey, and already we have traveled from absolute nothingness to the first light ever to travel freely through the cosmos. The universe is now 380,000 years old, a newborn by cosmic standards, and it is filled with hydrogen and helium, with that ancient afterglow of light, and with an almost perfect, featureless calm. Almost perfect, because hidden within that fog, tiny ripples, fluctuations in density no bigger than 1 part in 100,000, had been left behind by inflation. And those ripples, they were about to change everything. But that is a story for a little later. For now, let your breathing slow. Let the universe around you feel just a little more ancient, a little more vast. You are made of matter that has been here since those very first minutes. Rest in that thought. Let your body grow heavier. Let the sounds around you fade. We left our universe at a moment of quiet, a universe that had just become transparent for the very first time, filled with drifting clouds of hydrogen and helium, bathed in that faint ancient glow. It was in every direction featureless, calm, and almost completely dark. There were no stars yet, no galaxies, no light of any kind being generated anywhere, just an endlessly expanding ocean of gas, slowly thinning as space itself continued to stretch. Cosmologists have a name for this long, still chapter of history. They call it the Dark Ages. The cosmic Dark Ages lasted for an almost incomprehensible stretch of time, roughly 150 to 800 million years after the Big Bang. For hundreds of millions of years, the universe was simply dark. No star had yet ignited. No photon of visible light was being created anywhere. If you could have floated in space during this era, you would have seen nothing, not blackness dotted with stars, but a genuine, total, absolute darkness. A universe full of matter, full of potential, and yet producing not a single spark of light. But the darkness was not static. Quietly, invisibly, gravity was doing its patient work. Remember those tiny ripples we mentioned, those almost imperceptible fluctuations in density left behind by inflation. In some regions of the universe, there was ever so slightly more matter than in others, and gravity, relentless and unhurrying, began pulling that matter together. Over millions of years, tendrils of gas grew denser. Clumps formed within clumps. The universe was slowly, silently weaving itself into a vast web, a structure astronomers today call the cosmic web, a network of filaments and voids that stretches across the entire observable universe, like a three-dimensional spider's web of unimaginable scale. And then, after all that patient darkness, the first star was born. Deep inside one of those collapsing clouds of hydrogen, gravity squeezed the gas so tightly, and the pressure and temperature at the core climbed so high that something extraordinary happened. Hydrogen atoms began fusing together to form helium, releasing energy in the process. A nuclear fire ignited. the universe had made its first sun. These first stars were nothing like the sun you know. They were enormous, perhaps hundreds of times the mass of our own star, blazing with a ferocious blue-white light. Scientists call them population III stars, and they have never been directly observed. They burned so hot and lived so briefly that none remain. But we know they existed because the universe they left behind bears all the marks of their passing. These titanic first stars burned through their fuel at a reckless pace. While a star like our sun can burn for 10 billion years or more, a population III star may have lived for only a few million years, a blink of an eye in cosmic time. And when they died violently, collapsing and then erupting as supernovae, explosions so powerful they outshone entire galaxies for a brief moment. In those explosions, the first heavy elements were forged: carbon, oxygen, nitrogen, iron, elements that had never existed anywhere in the universe before. The cosmos had been made of only hydrogen and helium. Now, for the first time, it was becoming more complex. Those supernova explosions did something else too. They poured vast amounts of ultraviolet radiation out into the surrounding universe, and that radiation began to change the hydrogen gas drifting between the stars. The neutral hydrogen atoms, which had formed so peacefully 380,000 years after the Big Bang, began to be stripped of their electrons once more, ionized by the light of the first stars. This process, which unfolded over hundreds of millions of years, is called the epoch of reionization. Slowly, the universe transitioned from a fog of neutral hydrogen into the largely transparent, ionized medium that fills the space between galaxies today. The dark ages were ending. The universe was waking up. As you drift and rest, consider this. Every atom of carbon in your body, every atom of oxygen in your lungs right now, was forged inside a star that exploded billions of years before our sun was ever born. The iron in your blood was made in a stellar furnace. The calcium in your bones was scattered across space by a supernova. You are not separate from the universe, you are a part of it that has temporarily taken a very particular shape. The astronomer Carl Sagan put it simply: we are made of star stuff, and now we know that's not poetry. It is precise, literal astrophysical fact. While the first stars were blazing and dying, something else was growing in the densest regions of the cosmic web, the first galaxies. Gravity was drawing not just individual clouds of gas together, but enormous collections of them, millions and then billions of stars beginning to orbit a common center. The earliest galaxies were small and irregular compared to the grand spirals we see today. They were clumpy, chaotic, colliding and merging with one another constantly. Our own Milky Way galaxy is thought to have begun forming around 13.6 billion years ago, just 200 million years after the Big Bang, though it would take billions more years of mergers and growth to become the galaxy we live in today. At the heart of many of these early galaxies lurked something monstrous: supermassive black holes. How these giants formed so quickly in the early universe is one of the great unsolved mysteries of modern cosmology. Some may have grown from the collapsed remnants of those first enormous population III stars. Others may have formed through direct collapse of massive gas clouds. Whatever their origin, we know they existed, because we can see the light of the matter swirling around them, heating up as it falls inward and radiating with the brilliance of a trillion suns. We call these objects quasars, and some of the most distant light we have ever detected comes from quasars blazing in the young universe, over 13 billion light-years away. Through all of this, the dark ages, the first stars, the forming galaxies, something else was present that we haven't yet spoken of. Something invisible, something that produces no light and absorbs no light, and yet makes up roughly 27% of all the mass and energy in the universe. Scientists call it dark matter. We cannot see it, we cannot touch it. But we know it exists because of the gravitational influence it exerts on everything around it. Without dark matter, galaxies as we know them could not exist. The ordinary matter alone would not have enough gravity to pull itself together in the way we observe. Dark matter was the invisible scaffolding on which the first structures of the universe were built, and it remains woven through every galaxy, including our own, to this day. The universe is now in our story around 1 billion years old. It is no longer dark. It is threaded with light, ancient starlight, the glow of quasars, the slow bloom of young galaxies finding their shape. The cosmic web is coming into focus, and gravity, that quiet, patient force, is still pulling, still drawing matter together, still building structure from chaos. Somewhere out in a particular spiral arm of a particular unremarkable galaxy, the atoms that will one day become our Sun and our Earth are still scattered across space, drifting in clouds, waiting for their moment. That moment is coming, but not yet. For now, let the darkness of the cosmos wrap around you like a blanket. You are ancient, you are stardust, and you are exactly where you're meant to be. Rest now. Breathe slowly, let your thoughts soften at their edges. We have traveled a long way together through the dark, through the silence of the cosmic ages, through the first blazing of stars, through the slow weaving of galaxies. Tonight we move closer to home, much closer. We are now going to zoom in past billions of galaxies, past billions of stars, to one particular cloud of gas and dust drifting in an outer arm of the Milky Way. It is an unremarkable cloud by cosmic standards, cold, diffuse, slowly rotating. But inside it is everything that will one day become our Sun, our Earth, the oceans, the mountains, and every living thing that has ever drawn breath. We just have to wait for gravity to work its quiet magic one more time. Our solar system began forming approximately 4.6 billion years ago, roughly 9 billion years after the Big Bang. That gap matters. It took the universe 9 billion years of star birth and star death, of supernovae scattering heavy elements into space, of those elements mixing and drifting and accumulating in new clouds, before the conditions were right for a star like our Sun to exist. Our Sun is what astronomers call a population-ized star, a third-generation star, enriched with the heavy elements forged by generations of stellar ancestors. It is, in the most literal sense, built from the ruins of older dead stars. The trigger for our solar system's birth may have been a nearby supernova, a dying star whose shockwave rippled through that cold molecular cloud and compressed it just enough to tip it over the edge. Gravity did the rest. The cloud began to collapse inward, slowly at first, then faster. As it fell inward, it began to spin, and as it spun, it flattened, the same way a ball of pizza dough flattens when you spin it. That spinning, flattening disk of gas and dust is called a solar nebula, and it is the cradle from which everything in our solar system was born. The Sun, the planets, the moons, the asteroids, the comets, all of it emerged from a single collapsing cloud. At the center of that collapsing disk, matter piled up faster than anywhere else. The pressure and temperature climbed, and then about 4.6 billion years ago, the core grew hot enough and dense enough for nuclear fusion to begin. Hydrogen atoms began fusing into helium, releasing energy. A new star switched on. Our Sun was born. It was not a dramatic explosion visible across the galaxy. It was a slow ignition, a gradual brightening, a star finding its balance between the inward pull of gravity and the outward push of the energy it was now generating. That balance, once found, has held for 4.6 billion years and will hold for roughly 5 billion more. While the Sun was igniting at the center, the material in the surrounding disk was not sitting still. Dust grains collided and stuck together, forming pebbles. Pebbles collided and formed boulders. Boulders collided and formed bodies kilometers across, which scientists call planetesimals. And those planetesimals in turn crashed and merged over millions of years to form the planets. This process, called accretion, is slow and violent in equal measure. The early solar system was a chaotic demolition derby, with countless bodies smashing into one another, some shattering, some merging, slowly but relentlessly building the worlds we know today. Earth itself formed around 4.5 billion years ago, and its earliest days were nothing like the world we know. The young Earth was a hellish place. its surface a churning ocean of molten rock, bombarded constantly by asteroids and meteorites raining down from the chaotic debris field of the early solar system. This era has a name, the Hadean Aeon, named after Hades, the Greek underworld. And yet even in that furnace of a world, something was being built. The heaviest elements, iron and nickel, sank toward the center, forming Earth's core. Lighter silicate rock rose to the surface. Our planet was differentiating, separating into layers, becoming the structured world it is today. About 4.5 billion years ago, while the Earth was still young and partially molten, something cataclysmic happened. A body roughly the size of Mars, which scientists have named Theia, collided with the early Earth in a glancing blow of almost unimaginable violence. The impact vaporized much of both bodies. A vast cloud of molten rock and debris was flung into orbit around the Earth. And over time, that debris came together through the same process of accretion that built the planets and formed the Moon. The Moon, which has guided human calendars and stirred the tides for all of human history, was born from a planetary collision. It is, in a very real sense, a piece of the Earth itself. In the outer solar system, the giant planets Jupiter, Saturn, Uranus, Neptune were forming from the same disk of material, but in a region cold enough that ices could survive: water ice, methane ice, ammonia. This gave them access to far more material than the rocky inner planets, and they grew enormous. Jupiter alone contains more mass than all the other planets in the solar system combined. And Jupiter's enormous gravity had consequences. It flung countless asteroids and comets on wild trajectories, sending them careening inward toward the inner solar system. Some of this bombardment was catastrophic, but some of those incoming bodies carried something precious: water and complex organic molecules, the chemical building blocks of life. By around 4.4 billion years ago, just 100 million years after the Earth formed, evidence suggests that liquid water was already present on our planet's surface. We know this because of tiny crystals called zircons, found in ancient rocks in Australia, which can be dated with extraordinary precision. Some of these zircons are 4.4 billion years old, and the chemistry locked inside them tells us they formed in the presence of liquid water. The oceans of Earth are ancient beyond imagining, older than the oldest mountains, older than the first continents as we know them, almost as old as the planet itself. And so we arrive at a world that is beginning, against all odds, to be hospitable. A world with a molten iron core generating a magnetic field, a shield that will one day protect life from the worst of the sun's radiation. A world with liquid water pooling in basins. A world already carrying in its rocks and in its oceans the complex carbon molecules that are the alphabet of life. The universe has spent 9.1 billion years building the conditions for this moment. The stage is set, the chemistry is present, and somewhere in some quiet tide pool or deep-sea vent, the most improbable thing in the known universe is about to happen. We have come so far, you and I, from a universe that had no space, no time, no matter, all the way to a small blue world cooling in the light of a young star. And yet in all the universe, in all those hundreds of billions of galaxies, each with their hundreds of billions of stars, this particular world on this particular evening is the one you happen to be resting on. That is not nothing, that is everything. Let your weight sink deeper into wherever you're lying. The Earth is holding you, the same Earth that was forged in fire, shaped by collision and patient enough to wait 4.5 billion years to be ready. It has you now. Rest. The story of life itself begins in our next chapter. Feel the stillness around you, the slow, deep quiet of a world at rest. That is how we find the early Earth, not silent exactly, but vast and patient. The oceans are warm in places, heated from below by a planet still cooling from its violent birth. The sky is a haze of carbon dioxide and nitrogen. There is no oxygen to breathe, no ozone layer to soften the sun's ultraviolet rays. The land where it exists is bare grey rock, no moss, no soil, no sound of wind through leaves. And yet something is stirring. In the chemistry of those ancient seas, in the warmth of underwater vents and tidal shallows, the molecules of life are assembling themselves, slowly, blindly, through nothing more than the laws of physics and the restless creativity of chemistry. What happens next is the most consequential event in the history of our planet. The first life on Earth appeared approximately 3.8 billion years ago, possibly earlier. We know this from microscopic fossils found in ancient rock formations in Greenland and Western Australia, where some of the oldest surviving stone on the planet is preserved. These earliest life forms were not animals, not plants, not anything with a shape we would recognize. They were single cells, tiny membrane-bound pockets of chemistry, capable of two things that set them apart from everything that had come before. They could harvest energy from their environment, and they could copy themselves. That ability to replicate, to pass information from one generation to the next, is the thread that connects those first cells to every living thing on Earth today, including you. Where did life begin? This is one of the most debated questions in all of science, and the honest answer is that we do not yet know for certain. One compelling idea is that life first emerged at hydrothermal vents, cracks in the ocean floor where superheated, mineral-rich water seeps up from the Earth's interior. These vents would have provided a constant source of chemical energy, a stable, warm environment shielded from the bombardment still raining down on the surface, and a rich cocktail of the molecules needed to build the first cells. Today, hydrothermal vents on the ocean floor teem with life, creatures that survive without sunlight, feeding entirely on chemical energy. They may be the closest living relatives of the very first organisms that ever existed. For the first 2 billion years of life on Earth, every living thing was a single cell. No eyes, no limbs, no brains, just microscopic specks of life drifting through ancient oceans, dividing and surviving and slowly, generation by generation, evolving. It can feel like nothing much was happening, but this is misleading. During those 2 billion years, life was solving some of the hardest problems in the history of biology. It was inventing the machinery of the cell, the proteins, the membranes, the molecular motors, the intricate chemical pathways that every living cell on Earth still uses today. The single-celled world was not a waiting room for real life. It was life, extraordinary, inventive, and utterly foundational to everything that followed. Around 2.7 billion years ago, a particular group of microorganisms appeared that would change the planet forever. They were called cyanobacteria, and they had evolved the ability to do something no life had managed before, to capture sunlight directly and use its energy to power their chemistry, releasing oxygen as a byproduct. This process, photosynthesis, seems unremarkable until you consider what it meant for the planet. For hundreds of millions of years, these tiny organisms pumped oxygen into an atmosphere that had contained almost none. By around 2.4 billion years ago, oxygen levels had risen dramatically in an event called the Great Oxidation Event. For most life at the time, this was catastrophic. Oxygen was toxic to organisms that had evolved without it. But for a new kind of life waiting in the wings, it was an invitation. That invitation was answered by the evolution of a new kind of cell, one with a profound difference from everything that had come before. Earlier cells, called prokaryotes, kept their genetic material floating freely inside them. But around 2 billion years ago, a new type of cell appeared. The eukaryote, a cell with a distinct nucleus, a protected inner chamber where the DNA was housed. Even more remarkably, eukaryotic cells contain tiny structures called mitochondria, which are almost certainly the remnants of ancient bacteria that were once engulfed by a larger cell, and rather than being digested, formed a permanent partnership. Mitochondria became the cell's power plant, breaking down oxygen to release energy. Every animal, every plant, every fungus on Earth today is made of eukaryotic cells. Every one of us is, at our most fundamental level, a collaboration between ancient organisms. For another billion years or so, even eukaryotic life remained largely single-celled. And then, roughly 600 to 800 million years ago, something happened that opened an entirely new chapter in the story of life. Cells began staying together after dividing. They began specializing, different cells doing different jobs, some sensing light, some digesting food, some providing structure. Multicellular life had arrived. The first animals were soft, strange creatures, some resembling fronds or discs, unlike anything alive today. They left no hard shells or bones to fossilize, only impressions in the seafloor mud, but they were there. And the universe, which had begun as a single point of infinite density, had now produced something that could, in however primitive a way, experience the world around it. Then came one of the most dramatic episodes in the history of life, the Cambrian explosion. Around 538 million years ago, in a geological instant, a period of perhaps 20 to 25 million years, the fossil record suddenly fills with an extraordinary diversity of complex animal life. Creatures with eyes, with legs, with shells, with claws, with mouths. The basic body plans of almost every major animal group alive today appeared within this relatively brief window. No one is entirely sure what triggered it: rising oxygen levels, changes in ocean chemistry, a developmental innovation in how genes controlled body shape, perhaps all of these together. But the effect was unmistakable. Life, which had spent billions of years experimenting quietly, suddenly burst into spectacular variety. Among the creatures of the Cambrian seas was a small, soft-bodied swimmer, little more than a tube with a primitive notochord running along its back, unremarkable by any measure. And yet this creature, or something very like it, was the ancestor of every vertebrate that has ever lived. Every fish, every amphibian, every reptile, every bird, every mammal, including the one lying quietly wherever you are right now, traces its lineage back to that modest, anonymous swimmer in a Cambrian sea over 500 million years ago. The line from that creature to you has never once broken. Every single generation, without exception, survived long enough to reproduce. That is the chain you are the latest link in. Life has not had an easy journey. In the 538 million years since the Cambrian explosion, Earth has suffered 5 mass extinction events, moments when the vast majority of species on Earth were wiped out in a geological heartbeat. The worst of these, around 252 million years ago, killed an estimated 96% of all marine species and 70% of all land vertebrates. It is called the Great Dying. And yet life endured. A stubborn remnant always survived, hidden in some sheltered corner of the world. And from that remnant the whole rich tapestry of life rebuilt itself, stranger and more varied than before. Extinction, it turns out, is not only destruction. It is also an opening, a clearing of the stage that allows new forms to rise that never could have thrived in the shadow of what came before. And so here we are, 13.8 billion years from a universe with no space, no time, no matter. 4.6 billion years from a swirling cloud of gas and dust. 3.8 billion years from the first trembling chemistry of life. And 538 million years from the first creatures that looked, however dimly, at the world around them. The story is long, it is ancient beyond imagining, and it has been heading, through all its detours and disasters, in a direction that eventually leads here, to this room, to this breath, to the quiet rise and fall of your chest in the dark. You are the universe becoming aware of itself, and tonight the universe is resting. Let yourself. The next chapter, the long walk toward us, begins when you're ready. Let your breathing be easy and slow. In and out, there is nowhere you need to be, nothing you need to do. Just drift the way life once drifted through ancient seas, unhurried, guided by nothing more than the slow turning of the world. We pick up our story around 500 million years ago. The oceans are rich and strange, filled with trilobites armored like little tanks, with early fish exploring the open water, with forests of coral and waving sea creatures anchored to the seafloor. The land, meanwhile, is still almost entirely bare. Vast empty continents of naked rock stretch under an open sky. But life, as it always does, is looking for somewhere new to go. And the land, with its abundant sunlight and its untouched resources, is waiting. The first organisms to colonize the land were not animals. They were plants, or rather the distant ancestors of plants, simple green algae that crept from shallow coastal waters onto damp rock, gradually evolving the ability to survive in open air. By around 470 million years ago, the first true land plants had appeared, small, mat-like organisms without roots or leaves, clinging to the edges of rivers and lakes. They were modest pioneers, but they changed the world profoundly. As they spread, they began breaking rock into soil, pumping oxygen into the air, and creating the first thin layer of living green across a previously barren planet. Every meadow, every forest, every field of wheat that has ever fed a human being traces its lineage back to those first tentative green mats on ancient stone. Animals followed, drawn by the food and shelter the spreading plants provided. The first animals to make the crossing from sea to land were arthropods, creatures related to today's insects and spiders, which scrambled ashore around 430 million years ago. But the crossing that would most directly shape our own story came around 375 million years ago, when a group of fish with unusually strong, fleshy fins began hauling themselves through shallow swamps. These creatures, the most famous of which is called Tiktaalik, discovered in Arctic Canada in 2004, were neither fully fish nor fully land animal. They had gills and scales, but also a neck, ribs, and fins that functioned something like primitive limbs. They could prop themselves up. They could breathe air. They were, in a very real sense, the first of us to feel solid ground beneath our bodies. Over the next tens of millions of years, those fish-descended pioneers diversified into the first amphibians, creatures that could live on land but still needed water to lay their eggs. And then came a crucial innovation, the amniotic egg. Around 310 million years ago, certain animals evolved eggs with a tough, waterproof shell and a self-contained package of fluid and nutrients inside, everything an embryo needed to develop without being submerged in water. This was a liberation. Suddenly, animals could reproduce far from rivers and lakes. They could spread into dry, rocky interiors that had been entirely inaccessible before. The egg, unremarkable as it seems, was one of the great inventions in the history of life, and it is the reason reptiles, birds, and the earliest mammals were able to conquer the land so completely. By around 300 million years ago, the continents of Earth were joined together into a single vast landmass, a supercontinent scientists call Pangaea. Imagine standing at its center. You would be thousands of kilometers from any ocean, surrounded by hot, dry desert with no sea breeze to moderate the climate. Pangaea created conditions of extreme heat in its interior and enormous, powerful seasonal monsoons along its coasts. Life adapted as it always does, and as Pangaea slowly began to break apart, a process that started around 200 million years ago and continued for over 100 million years, the separating landmasses carried their populations of animals and plants with them, like passengers on the world's slowest ships. That is why you can find related species on continents that are today separated by entire oceans. They were once neighbors on the same great land. It was on Pangaea, and in the world that followed its breakup, that the dinosaurs rose to dominance. They first appeared around 230 million years ago, not as giants, but as relatively modest creatures, quick on their feet, benefiting from the ecological vacuum left by the great dying extinction we mentioned earlier. Over the following millions of years, they diversified into an astonishing array of forms. Vast, long-necked herbivores that moved like living mountains, swift, feathered predators, armored tanks with spiked tails, creatures with crests and frills and shapes that seem almost too strange to be real. For 165 million years, dinosaurs were the dominant large animals on Earth. To put that in perspective, the entire span of human existence, from our earliest ancestors to today, is less than 1/10 of the time the dinosaurs ruled. And yet, even during the age of the dinosaurs, another story was unfolding quietly in the shadows. The first mammals had appeared around 225 million years ago, small, mostly nocturnal creatures, warm-blooded and covered in fur, scurrying through the undergrowth and nesting in burrows while the great reptiles thundered above them. For most of the Mesozoic era, mammals remained small and marginal, but their smallness was, in a strange way, their salvation. They were hiding, they were surviving, they were waiting, though they did not know it, for an opening that would one day allow them to inherit a world. That opening came 66 million years ago, when an asteroid approximately 10 to 15 kilometers wide struck what is now the Yucatan Peninsula of Mexico at a speed of around 20 kilometers per second. The impact released more energy than 1 billion nuclear bombs. It triggered wildfires across entire continents, sent a plume of vaporized rock and dust into the upper atmosphere that blocked sunlight for years, caused global temperatures to plummet, and collapsed the food chains that the great dinosaurs depended on. Within a geologically short time, all non-avian dinosaurs were gone, along with roughly 3/4 of all species on Earth. It was catastrophic, it was devastating, and for the small, warm-blooded, burrowing mammals huddled in the cold and dark, it was eventually the beginning of everything. In the aftermath of the extinction, mammals found themselves in a world emptied of its dominant creatures, a world full of ecological niches waiting to be filled, and fill them they did with breathtaking speed by evolutionary standards. Within 10 million years of the asteroid impact, mammals had diversified into an extraordinary range of forms. Early ancestors of horses, whales, bats, elephants, and primates had all appeared. The warm-blooded, live-birth, milk-feeding body plan that had kept mammals alive and small through the age of dinosaurs now proved extraordinarily versatile. Mammals took to the sky, they returned to the sea, they climbed into the trees. The world that the asteroid had emptied became, in geological time, remarkably full again. Among those mammals that took to the trees were the primates, small, agile creatures with forward-facing eyes for judging distances in the canopy and grasping hands for gripping branches. The earliest primates appeared around 55 to 60 million years ago. They were nothing like us yet, but in the trees something was being shaped that would eventually produce the most consequential creature this planet has ever known. Living in the complex three-dimensional world of the forest canopy requires quick decisions, social intelligence, the ability to remember which branch leads where and who among your group can be trusted. The forest was, in a very real sense, the classroom in which primate intelligence was gradually, over tens of millions of years, being built. We are getting closer now, from the first trembling mats of green on bare rock, to fish hauling themselves onto land, to small mammals surviving in the dark beneath the feet of giants, to the first wide-eyed primates peering through ancient leaves. Each step has been both unlikely and inevitable, a chain of accidents and adaptations stretching across hundreds of millions of years, each link holding just long enough to pass something forward. What it passed forward ultimately was you. You are the inheritor of all of it, every adaptation, every survival, every narrow escape from extinction. The whole long, improbable story has been quietly building toward a creature that can lie still in the dark and wonder about its own beginnings. Let that thought carry you gently now like a current. The story of our own ancestors begins just ahead, but sleep first, sleep. Let the weight of your body feel heavy and warm. There is nothing pulling at you tonight, no urgency, no noise, just the slow and ancient rhythm of rest. We have been traveling together for a long time now, you and I, across billions of years, through fires and extinctions and the patient work of evolution. Tonight we arrive somewhere that should feel in a quiet way familiar. We are almost home. We are in Africa. The time is somewhere between 7 and 5 million years ago. The climate is shifting. Forests that once spread across vast stretches of the continent are contracting, replaced by open grassland and savanna. In the trees at the forest edge, a group of apes is living the life their ancestors have lived for millions of years. But the trees are growing fewer, the open ground is growing wider, and some of them are beginning, tentatively, to step out into it. Between 5 and 7 million years ago, the evolutionary lineage that would eventually lead to humans split from the lineage that would lead to our closest living relatives, chimpanzees and bonobos. This split did not happen in a single dramatic moment. It was a slow, gradual divergence over hundreds of thousands of years, populations separating and occasionally mixing again before finally going their own ways. The creatures on our side of that split are called hominins, and what distinguished them early on was not a bigger brain or the use of tools. It was something far more fundamental and far more visible. They began to walk upright on two legs. Bipedalism, walking on 2 feet, is one of the defining characteristics of the human lineage, and it appeared millions of years before our brains grew to anything like their current size. Walking upright had profound consequences. It freed the hands entirely from the business of moving hands that could now be used for carrying, for making, for gesturing, for eventually crafting tools with a precision no other animal could match. It also changed what our ancestors could see standing tall above the grass, scanning the horizon for predators and prey, but it came with costs too. Upright walking is actually less efficient than moving on all fours, and it placed enormous strain on the lower back, the knees, the hips, problems that millions of humans still live with today. The aching back you may have felt at some point in your life is, in the most direct sense, an inheritance from the savannah. Your skeleton was redesigned in a hurry, evolutionarily speaking, and the joins still show. One of the most famous of our early ancestors is a creature known as Australopithecus, a group of hominins that lived in Africa between roughly 4 and 2 million years ago. The most celebrated individual is a female discovered in Ethiopia in 1974, given the name Lucy by the scientists who found her, after the Beatles' song playing in their camp that night. Lucy walked upright, stood just over a meter tall, and had a brain roughly a third the size of ours. She climbed trees with ease but spent much of her life on the ground. She was neither ape nor human in the way we think of those categories. She was something in between, something the world had never seen before, and she is one of the clearest windows we have into what our own ancestors looked and lived like 3.5 million years ago. Around 2.6 million years ago, something new appeared in the archaeological record: stone tools. Simple ones, rocks deliberately struck against other rocks to create a sharp edge. But the appearance of intentional tool-making marks a profound threshold. It suggests a mind capable of planning ahead, of seeing a future use for a shaped object, of holding an idea and then making it physical. The toolmakers of this era belong to the genus Homo, our own genus, and their tools, called the Alderman Toolkit, allowed them to access food in ways no other animal could. They could crack open bones for marrow. They could butcher large animals. A new kind of creature was emerging, one that did not simply adapt to the world but had begun in its small way to reshape it. Over the next 2 million years, the human family tree grew complex, a branching, tangled bush of different hominin species living alongside one another, sometimes in the same landscapes, sometimes interbreeding. There was Homo erectus, who appeared around 1.9 million years ago and was the first of our ancestors to leave Africa, spreading across Asia and into Europe. Tall, long-legged, with a brain significantly larger than earlier hominins, Homo erectus was a remarkably successful species, surviving for nearly 2 million years, far longer than our own species has existed yet. There was Homo heidelbergensis, thought to be the common ancestor of both modern humans and the Neanderthals. There were the Denisovans, known to us only from a fragment of finger bone and a few teeth found in a Siberian cave. The story of human evolution is not a single straight line. It is a conversation between many different peoples, across many different landscapes, over an almost incomprehensible stretch of time. Among all the changes that shaped the human lineage, perhaps none was more transformative than the control of fire. Evidence suggests our ancestors were using fire at least 1 million years ago, and possibly much earlier. Fire meant warmth in cold climates, protection from predators, and light in the darkness. But its deepest effect may have been on our food. Cooking breaks down the tough fibers in meat and plant material, making it far easier to digest and unlocking far more calories from the same amount of food. Some scientists believe that cooking is what allowed our brains to grow so large, because a bigger brain demands enormous energy, and cooking effectively predigests food, making that energy available. In this view, every great thought ever thought, every poem ever written, every equation ever solved was made possible in part by the discovery of cooking. Our own species, Homo sapiens, appeared in Africa around 300,000 years ago. We know this from fossil remains found in Morocco at a site called Jebel Irhoud, which pushed back the known origins of our species by over 100,000 years when they were dated in 2017. These earliest members of our species looked broadly like us, high rounded skulls, flat faces, though the shape of the brain case suggests their minds were still developing toward the form we carry today. They were us and yet not quite us. The species was new. The full flowering of what our minds could do was still to come. For most of our species' existence, we lived as hunter-gatherers, small mobile bands of people moving across landscapes, following the seasons, reading the land with an intimacy that modern people have largely lost. And we were not alone. For tens of thousands of years, Homo sapiens lived alongside Neanderthals in Europe and the Middle East, and alongside Denisovans in Asia. We now know from ancient DNA analysis that these groups did not simply coexist, they interbred. Most people alive today outside of sub-Saharan Africa carry somewhere between 1 and 4% Neanderthal DNA. The Neanderthals are not entirely gone. They live on in small but measurable ways in the genome of nearly every person on Earth. Around 70,000 years ago, something shifted in the behavior of our species that archaeologists call the cognitive revolution, though whether it was truly a sudden change or a gradual accumulation, we still debate. What we see in the archaeological record is an explosion of symbolic behavior: jewelry made from shells, pigments used to decorate bodies and objects, musical instruments carved from bone, and eventually, on the walls of deep caves, paintings of animals so vivid and alive that they still move people to tears today. Our ancestors were not just surviving, they were expressing something, telling stories, making beauty, reaching beyond the immediate and the practical towards something that had no survival value whatsoever, except that it made life feel meaningful. We had become, in the fullest sense, human. Think about that for a moment as you rest. Somewhere between 40,000 and 17,000 years ago, a person, someone with a mind shaped by the same deep history as yours, crawled into a cave in what is now France or Spain, mixed pigment by the light of a small flame, and painted a horse or a bison on the wall. Not because it fed them, not because it kept them warm, but because something in them needed to make it. Needed to say, I was here, I saw this, this is what the world looked like to me. That impulse has not gone anywhere. It is still in you. It is what makes you curious about your own origins, what brought you to this story tonight. You are the latest expression of something 13.8 billion years in the making, a universe that learned to paint, a cosmos that learned to wonder. Rest now in that knowledge. The final chapters of our story, civilization, discovery, and the great questions that remain are waiting quietly for you. But first, sleep. Breathe in slowly. Let your thoughts become loose and unhurried. We are nearing the end of our great journey now, not the end of the universe's story, which has billions of years still to run, but the end of the long road from the Big Bang to the world you know. The chapters ahead are shorter in time, but richer in detail. We are arriving at the human world, your world. We find ourselves in a region of the Middle East called the Fertile Crescent, a curve of land stretching from what is now Iraq, through Syria, Lebanon, and down into the Jordan Valley. The last ice age has ended. The climate has warmed. Grasses are growing in abundance across the hillsides, their heavy seed heads bowing in the breeze. And a group of people, perhaps almost by accident, perhaps through long observation and patient experiment, is about to discover something that will remake the human world entirely. Around 12,000 years ago, humans in the Fertile Crescent began to deliberately cultivate wild grasses, selecting the plants with the largest, most nutritious seeds, saving them, planting them, tending them. This was the birth of agriculture, and it is one of the most consequential developments in the entire history of our species. For the previous 290,000 years of our existence, every human being had been a hunter-gatherer, moving with the seasons, taking what the land offered. In a geological instant, just a few thousand years, that changed. People began staying in one place. Settlements grew, populations rose, and a way of life that had sustained our species for nearly its entire existence began to recede, replaced by something utterly new. Agriculture did not emerge in just one place. Independently, in several different parts of the world, people arrived at the same discovery within a few thousand years of one another. In China, where rice and millet were domesticated. In Mesoamerica, where maize was cultivated from a wild grass called teosinte. In the highlands of New Guinea, where taro and bananas were grown. In sub-Saharan Africa, where sorghum was farmed. This remarkable convergence, the same fundamental idea arising independently across the globe in a relatively short window of time, speaks to something universal in the human mind, and to the way the end of the last ice age created similar opportunities and pressures for people living in very different landscapes, half a world apart from one another. With settled farming came something that had never existed before in human history: surplus. For the first time, a community could produce more food than it needed to survive from one day to the next, and surplus changed everything. It meant that not everyone had to spend all of their time finding food. Some people could do other things. They could specialize. They could become potters, weavers, metalworkers, priests, soldiers, scribes. The division of labor that underlies all of modern society, the idea that different people do different jobs and trade their efforts with one another, grew directly from the grain stores of the first farming villages. The city, the state, the market, the army, the school, all of it flows ultimately from the decision to plant a seed and wait. The first true cities appeared in Mesopotamia, the land between the rivers Tigris and Euphrates in what is now Iraq, around 5,000 years ago. The city of Uruk is among the earliest we know of, and at its peak it may have housed 50,000 people or more, an almost unimaginable concentration of human beings by the standards of the time. Managing a city of that scale required something new, a system for keeping records. Who owned which field, how much grain was stored in the temple, what taxes were owed. And so around 3400 BCE, the people of Mesopotamia invented writing, not at first for poetry or history or prayer, but for accounting. The earliest written texts we have are receipts and inventories. The written word, that most profound of human technologies, began as a spreadsheet. Writing transformed the human relationship with time. Before writing, all knowledge, every story, every technique, every piece of wisdom had to be carried in a living human memory and passed from person to person by voice. If the people who held that knowledge died before they could pass it on, it was lost forever. Writing changed that. It allowed knowledge to outlive the person who held it. Ideas could now travel through time as well as space. A thought written down in Mesopotamia 5,000 years ago can still reach you tonight. The accumulated knowledge of every civilization that ever developed writing has, in principle, been available to every civilization that came after. We are not starting from scratch with each generation. We are standing on the shoulders of the dead. As civilizations grew and traded and competed, they drove one another forward in a kind of cultural acceleration. The Egyptians raised the pyramids, structures so precisely engineered that modern architects still marvel at them, beginning around 4,500 years ago. The ancient Greeks, between roughly 600 and 300 BCE, developed the foundations of mathematics, philosophy, and systematic observation of the natural world that would eventually grow into modern science. In the Islamic Golden Age, between the 8th and 14th centuries, scholars in Baghdad, Cairo, and Cordoba preserved and extended the knowledge of the ancient world, making advances in algebra, astronomy, medicine, and optics that Europe would not match for centuries. Every era of human history has had its flowering, its moment of extraordinary creative energy, and each one has built upon the last. Among all the intellectual achievements of the human story, one stands out for what it revealed about our place in the cosmos. For most of human history, the Earth was understood to be the fixed and unmoving center of everything, the sun, the moon, the planets and stars all revolving around us. Then in 1543, a Polish astronomer named Nicolaus Copernicus published a theory proposing the opposite, that the Earth moves around the sun. It was a radical demotion. Over the following century, Galileo Galilei pointed a telescope at the sky and saw moons orbiting Jupiter, proof that not everything in the heavens revolved around the Earth. And Johannes Kepler worked out the mathematical laws governing the orbits of the planets. The universe, it turned out, did not revolve around us. We were one small world orbiting one ordinary star in a cosmos of almost incomprehensible scale. The scientific revolution that followed Copernicus accelerated through the 17th and 18th centuries with breathtaking speed. Isaac Newton, building on the work of Galileo and Kepler, formulated the laws of gravity and motion, a mathematical framework so powerful it could describe the fall of an apple and the orbit of a planet with the same equations. For the first time in human history, the universe appeared to follow rules that human minds could discover, express in the language of mathematics, and use to make precise predictions about what would happen next. The idea that the universe is, at its heart, comprehensible, that it operates by laws rather than by whim, is perhaps the most important intellectual discovery our species has ever made. By the early 20th century, our picture of the universe had grown almost beyond imagining and was about to be overturned entirely once more. In 1915, Albert Einstein published his theory of general relativity, rewriting Newton's understanding of gravity not as a force pulling objects together, but as a curvature in the fabric of space and time itself. Massive objects, stars, planets, black holes, bend the space around them, and other objects follow those curves the way a marble rolls around the inside of a bowl. This was not just a refinement of Newton, it was a completely different way of understanding what space, time, and gravity actually are. And it had an extraordinary implication, one that Einstein himself initially refused to believe. The universe was not static, it was expanding, and if it was expanding, then running the film backward, it must once have been unimaginably small. The Big Bang was not yet named, but the idea had arrived. And so we find ourselves in this segment at an extraordinary closing of a circle. We began our story 13.8 billion years ago with a universe being born. And now, through the long, patient work of human civilization, through farmers and scribes, through philosophers and astronomers, through Newton and Einstein, we find our species finally capable of asking the question that frames this entire journey. Where did all of this come from? The answer is almost within reach. The science that would confirm the Big Bang and begin to fill in its details was just decades away. But we have come so far tonight. Let the ideas settle like sediment drifting slowly to the bottom of a still, deep lake. The discoveries that confirmed our cosmic origins and the mysteries that remain are waiting in the next chapter. For now, let your mind go quiet. You are resting in a universe that took nearly 14 billion years to produce a creature capable of understanding it. That is enough. Rest. Let the darkness behind your closed eyes be comfortable and wide. There is a particular kind of peace that comes not from having all the answers, but from being at ease with the questions, from sitting quietly at the edge of what is known, and simply looking out into the unknown without fear. That is where we find ourselves tonight. We have traveled together from the very beginning, from a universe with no space, no time, no matter, all the way through the first stars, the first life, the first cities, the first telescopes. And now we arrive at the frontier, the place where the maps run out, where the most brilliant minds on Earth stand together and say, honestly and with genuine wonder, we do not know, not yet. We have known for some time that the universe is expanding, but in 1998, two independent teams of astronomers made a discovery so surprising that it earned them the Nobel Prize. The expansion of the universe is not slowing down, it is speeding up. Something is pushing space apart faster and faster, working against the inward pull of gravity, something invisible, something that fills all of space uniformly, something that has no accepted explanation in our current understanding of physics. Scientists gave it a placeholder name, dark energy, and when they ran the numbers, the scale of it was staggering. Dark energy accounts for approximately 68% of all the energy content of the universe. The ordinary matter that makes up every star, every planet, every atom of your body, everything we can see and touch and measure, accounts for less than 5%. We live in a universe we do not understand the majority of. Dark energy joins dark matter, which we met earlier in our story, to form what cosmologists sometimes call the dark sector of the universe. Together, dark matter and dark energy account for roughly 95% of everything that exists. The atoms, the stars, the galaxies, the oceans, the mountains, every creature that has ever lived, all of it is assembled from the remaining 5%. Our entire familiar universe, everything that has ever been seen or touched or thought about, is a thin layer of foam floating on an ocean whose nature we do not yet understand. This is not cause for despair. It is perhaps the most extraordinary invitation in the history of science, an entire universe, most of it unknown, waiting to be explored. One of the deepest puzzles in all of cosmology is a question so fundamental it strikes at the very heart of why we exist at all. In the physics of the Big Bang, whenever matter is created, an equal amount of antimatter should be created alongside it, particles identical to ordinary matter in every way except for their opposite charge. When matter and antimatter meet, they annihilate each other in a burst of pure energy. If the Big Bang truly produced equal amounts of both, they should have cancelled each other out entirely, leaving a universe of pure energy and no matter whatsoever. No stars, no planets, no atoms, no us, and yet here we are. Somehow in the first moments of the universe, matter won by the slimmest of margins, roughly one extra particle of matter for every billion matter-antimatter pairs. We exist because of that tiny imbalance, and we still do not know why it occurred. Physics rests on two extraordinarily successful theories: general relativity, which describes the behavior of the very large, and quantum mechanics, which describes the behavior of the very small. Each has been tested to extraordinary precision. Each works, and yet they are fundamentally incompatible with each other. When physicists try to apply both theories simultaneously, as they must when describing the very first instant of the Big Bang, where the entire universe was both unimaginably small and unimaginably massive, the mathematics breaks down entirely, producing nonsensical infinities. A complete theory of nature, a framework that unifies gravity with the quantum world, is the greatest unsolved problem in theoretical physics. It has been sought for nearly a century. Brilliant minds have dedicated their lives to it, and it remains just out of reach. There is a boundary in the universe beyond which we cannot see, not because our telescopes are not powerful enough, but because of the nature of light and time. Light travels at a finite speed, and the universe has a finite age. This means that the light reaching us from the most distant objects has been traveling for nearly 13.8 billion years, and we cannot receive light from anything farther away than that, because that light has not had time to reach us yet. The universe we can observe, the observable universe, is a sphere roughly 93 billion light-years across, but the full universe almost certainly extends far beyond that horizon, perhaps infinitely. What lies beyond what we can see is entirely unknown. There may be regions so distant that they are moving away from us faster than light can cross the gap, forever beyond any possible observation. The universe may be vastly, perhaps incomprehensibly, larger than the part of it we can ever know. Some physicists have proposed that our universe may not be the only one. The idea of a multiverse, an ensemble of universes, each perhaps with different physical laws and constants, arises naturally from certain versions of inflationary theory, the same framework that explains the rapid expansion of the early universe. If inflation can happen once, the reasoning goes, it can happen many times in many places, producing bubble universes that never interact with one another. In some of those universes, the constants of nature might be slightly different, gravity a little stronger, the charge of the electron a little different, and in those universes, stars and galaxies and life as we know it could not exist. We live in one of the rare universes where the constants happen to be compatible with our existence. Whether this is a profound coincidence, a selection effect, or evidence of something deeper is a question that may never be fully answerable. Perhaps the most human of all the great unanswered questions, the one that touches most directly on the experience of lying here in the quiet dark, aware of being aware, is the question of life elsewhere in the universe. Our galaxy alone contains somewhere between 200 and 400 billion stars. Astronomers now know that most of those stars have planets. The number of potentially habitable worlds in the Milky Way alone runs into the billions. And the Milky Way is one of an estimated 2 trillion galaxies in the observable universe. The numbers are so vast that the existence of life elsewhere seems almost inevitable, and yet we have found no confirmed evidence of it. Not a signal, not a microbe, not a trace. The silence is one of the most profound puzzles in all of science. It is called the Fermi paradox, and it has no agreed answer. And what of the future of the universe itself? If dark energy continues to accelerate the expansion of space, the long-term fate of the cosmos is one of extraordinary, almost poetic loneliness. Galaxies that are currently visible to us will, over trillions of years, recede beyond our horizon, moving away faster than light can bridge the gap. The night sky will empty, stars will exhaust their fuel and go dark one by one. Black holes will remain for a time, vast, silent, slowly evaporating over timescales so long they make the current age of the universe seem like a single heartbeat, and then in a final, quiet fading nothing, a cold, dark, diffuse remnant of a universe that once blazed with the light of trillions of stars. Physicists call this the heat death of the universe. It is by any measure a very long way off, but it is, as best we understand, how the story ends. And yet, and this is perhaps the most quietly wonderful thing of all, in this vast, mostly dark, mostly cold, mostly empty universe, hurtling toward an ending measured in numbers so large they have no meaning in daily life, something remarkable is happening right now. On a small rocky planet orbiting an ordinary star in an outer arm of one unremarkable galaxy among 2 trillion, a species of upright walking, large-brained, tool-making, storytelling primates is building telescopes and pointing them at the sky. It is writing down what it finds, it is sharing what it learns, it is lying awake at night and lying here drifting toward sleep, wondering about its own origins with a kind of aching, open-hearted curiosity that may be the most extraordinary thing the universe has yet produced. You are that species, this is that planet, and this wondering, this reaching is not separate from the universe. It is the universe reaching toward an understanding of itself. We have one chapter left in our journey, one final gathering of the threads, the discoveries still being made, the missions still flying, the questions that the next generation of human minds will carry forward into a future we cannot yet see. The story is not finished, it never will be, and that in itself is a kind of gift. For now, let everything go. The questions will be here when you wake. The universe will still be expanding quietly in every direction at this very moment, carrying you with it, as it always has, as it always will. Breathe out, let go, sleep.